Okay, good day everyone, and welcome to this EMS webinar. I hope that you have performed a nice summer and nice holidays, and we are back on at work now. And so EMS is starting again to propose their webinars, starting today with the presentation of Davide Mattia. Davide Mattia is professor of chemical engineering and deputy dean in the faculty engineering at University of Bath. He graduated in materials and engineering 22 from the University Federico II in Italy, and performed his PhD in materials engineering at Drexel University in Philadelphia, USA. He joined Bath in 2008 as a lecturer and was promoted to full professor in 2016. His current research focuses on using membranes to address environmental challenges, including sustainable manufacturing of materials and the removal of organic micropollutants from water. He is a past Royal Academy in Engineering Research Fellow and currently holds an EPSRC Established Career Fellowship in Water Engineering and is the principal investigator of program Grant SynHiSel on highly selective membranes. His presentation today will focus on 3D printed ultrafiltration and nanofiltration composite membranes. Thank you very much.
Thank you very much, Marco, for the introduction. I'll go to the presentation now. Okay, hopefully you can, at the moment, oh, perfect, okay. Thank you, Marco, and for your kind introduction, and many thanks to European Membrane Society Council for inviting me to deliver this seminar today. It's a great pleasure, and it's always great to interact with the EMS. So I'll okay. So I'll just start saying a few words about Bath. If you don't know where we are, we're in the southwest of England. Where's this star? And it's a beautiful city of Roman origin. These are the Roman baths still standing, and it's a beautiful place to visit. So very welcome to come and visit the city and the university and talk about membrane research. So I'll start today talking a bit about 3D printing and how we learned how to use it in the preparation of membranes. Let me start with just saying what 3D printing is. Probably most of you are familiar with the concept, but the idea is that you create a three-dimensional object using software, for example, CAD, and then that three-dimensional object, like a vase here, is sliced in very thin layers, which are then digitally sent to a printer that prints layer by layer the physical object that resembles more or less the digital one. And I'll talk more about the more or less aspect in a couple of slides. This is the very basic concept of 3D printing, but actually there are many different technologies under the general term 3D printing. In case you want to know a bit more about that, about 5 years ago now, we published a paper in Journal Membrane Science on the different technologies of 3D printing that can be used for membrane preparation. It's getting a bit old now as a paper, and this is a field 3D printing that is advancing very, very quickly. Let me start with focusing now on 3D printing for membranes. What are the opportunities and the challenges? I think the first point is that in terms of opportunities is that you can create complex functional structures integrating different materials, polymers, ceramic, metals. And so the promise of 3D printing is that you can go beyond the relatively narrow set of materials and shapes that you can achieve with traditional fabrication method, phase inversion, or interfacial polymerization. You can pretty much get a sheet, a hollow fiber, or a tube. You can, with these 3D printing technology, you can actually create very complex shapes, and that is sort of liberating, I think, for membranes where the material shape limitation has somewhat constricted the field, in my opinion. The challenge is very simple, and it's resolution. At the moment, there's no technology that can 3D print a pore in the UF or nanofiltration range. All have best resolution is in the order of perhaps 100 nanometers. There is a technology called two-photon polymerization that can go perhaps to the tens of nanometers, but it wouldn't allow you to print any sizable membrane. So we need to go around this key limitation of the technology, and the rest of my presentation is really about how you use the advantages and the opportunities of 3D printing while circumnavigating the challenges, in particular resolution. So there are a few key aspects that we learned as we started this work several years ago, which I think is useful to share with you when approaching 3D printing of membranes. So the first step when you're printing an object is to create a digital drawing of, say, if you want to print membrane, a digital object of a porous structure. And this introduces the concept of discretization. So what appears like a perfect circle on your screen in reality is actually a polygonal structure that approximates a circle. And so when we started doing this research, we thought, well, we could print triangular, rectangular, hexagonal, or circular cross-section pores and see the effect that that has on permeance. When we actually went to print these different structures from CAD, you see that more or less you get the same printed objects. You can't really distinguish a triangular structure from an hexagonal one. And so you have to take account of the distance between modeling and practical limitations of your printer. The second point is digital resolution. So when you're discretizing, say, a pore, or in this case a sphere, that will be discretized as many triangles. And of course, the more triangles you have, the closer you have to a perfect sphere or a perfect pore, but nonetheless, it will never be an ideal circle or sphere. An example you see here, from going from left to right, this is the exact same porous structure in CAD, but as we go from left to right, we increase the resolution, and you can see that at the rightmost image, you have very well-defined pores and this tortuosity, which I'll talk about later. However, this has an effect. And so you can imagine that you always want the highest possible digital resolution. But this also has a practical effect. So this image on the left is 50 megabytes, and it takes about 6 hours to print. This would be a number of 47 millimeter disc membranes. If you go to the image on the right, this file now has grown to 1.8 gigabytes, and it takes about 72 hours to print. So the higher the digital resolution, the more memory, so the more powerful computer you need, more powerful printer, 3D printer you need, and it takes more time to print it. And finally, there is the physical resolution of your printer. So what you see on the left, this is the digital object of our 3D printed membrane. And you can see it has very regular shape, very good circular pores. And this is what you obtain when you print. Consider these images are now a few years old, but at the time, this was a top-of-the-line commercial industrial 3D printer with a nominal resolution of 16 micrometers. And in reality, actually, the resolution was significantly poorer than that. But you can see that the numbers are not exactly of the printed object, are not exactly what were in the digital object, but nonetheless, you get that kind of shape. Finally, a key thing of the limitations of physical resolution of the printer is that you get quite a lot of macro and microscopic roughness. And you see it in these images here. Rather than a perfect circle, you're getting some roughness here. And what you see this image on the top right, image C, this is a cross-section of the pore in B. And you can see that throughout the length of the pore, you have roughness. Now, this could be a bad thing for a certain application, but you could also try to use this to your advantage in a different application. So, but you need to be aware of the fact that there's an element of roughness coming from the limitations of the printer's resolution. Now, the technology is advancing very fast, so you can imagine in a few years' time, we might be able to print objects with resolution in the, say, ultrafiltration or nanofiltration range for a membrane and with a much smoother surface, but we are not there yet. Okay, so these were the sort of lessons learned over time in our work. Now let me go to some actual membrane results. So the first part of the talk is on 3D printed ultrafiltration composite membranes. Now, the idea behind this is membrane patterning, which has been around for a long time. So what you see here, these are papers from about 10 years ago, where they used stamps to pattern an existing polymeric membrane to have this undulated structure, or to have, for example, if you had a pyramidal pattern, you could actually create these pyramidal stamps in the membrane. And what is interesting is that these undulations actually generate localized turbulence on the surface of the membrane, and that helps with reducing the adhesion of foulants and also in making it easier to dislodge the foulants when you're cleaning. However, this has some limitations you are, once you're patterning the membrane, you are distorting the surface, and so you can have losses in terms of permeance or selectivity. So what you can do with a 3D printer is design a membrane that has the patterning from the start without having to use a stamp to deform the membrane, and that allows you to have to avoid the drawbacks of patterning but get the advantages. So what we did is we started with computational fluid dynamics, thinking of a double sinusoidal structure like the images you see in the top left. What you see on the right here, this is the streamlines from CFD. So far away from the membrane, there's no distortion, you have laminar flow. When you get towards the surface of the membrane, which is this structure here, you can see that you start having some distortion, in particular in the valley of the 3D printed membrane, you have the formation of vortices. And so this is a formation of turbulence that help dislodge fouling from the surface of the membrane or to slow down its accumulation. And you can design this double sinusoidal structure with a simple equation shown at the bottom left of the slide by controlling two key parameters. One is the peak amplitude, which is the height of the peaks and troughs in the membrane, and the other is the wavelength, which is the difference between two peaks. So what you get when you make a map of the peak amplitude versus the wavelength, you can calculate the shear stress, which is given here in these different colors in this 2D plot. The shear stress you have at the surface of the membrane. You want the possible highest shear because that means that there's more force acting to dislodge fouling. So in principle, you would like to have to use a very high peak and very short wavelength, so something very pointy and very close to each other. However, if you look at CFD, if you are in this area where you have these very pointy peaks or troughs, which is represented by this the second CFD plot on the left, you have lots of secondary recirculation zones. So in fact, rather than minimizing fouling, you're actually increasing fouling. So all this area here at the top cannot really be used because it defeats the purpose of minimizing fouling. If you actually go at the bottom, where you have very shallow peaks and troughs, there's really no turbulence happening. And so again, it's like if you had a flat membrane. Oh, sorry. So in practice, the area where you want to operate is this operating zone in this area here. The next step to consider is fabricating your membrane. So the way we made our membranes is we 3D printed this wavy support, and then we deposited a selective layer which was made in PES by phase inversion on top of the 3D printed structure. And what you form is a conformal coating. So the PES selective layer takes the same shape of the wavy support. And so now you have to consider the fact that if your peaks are too high, or if the distance between peaks is too high, you will not be able to get a conformal coating of the PES. And so your actual area where you can get a high quality membrane is this smaller red rectangle. And eventually we try to get the highest possible shear within this area, which is represented by the red dot. And at the bottom left, this is the final membrane we get, where you can see that you have a PES selective layer on top of the 3D printed wavy support, and that the PES makes a conformal coating with the PES wavy with the printed wavy support. So we did a bit of characterization. So this is at the top left, you have the 3D printed support. On the top right, you have an SEM micrograph of the PES layer on top of the 3D printed support. And you can see that the PES layer forms a conformal coating onto the 3D printed support, even acquiring its underlying roughness. If you look at the cross section on the bottom left, you can see very clearly that you have the brighter area, which is the selective layer, and then the underlying slightly less bright PES support. And at the right, 3D printed support, excuse me. On the right, you can see a cross section of the PES support with the classical structure you obtain from phase inversion. And in terms of performance, you can see that the composite membrane takes some of its characteristics from the selective layer, like the porosity, the molecular weight cutoff, and the contact angle. But then the roughness is an average of the selective layer and the membrane support. So let me show you now some results. What you see here are two rows of results for oil and water emulsion done in cross-flow using a flat membrane at the top and a wavy membrane at the bottom. So both have the same PS selective layer, but one is flat and the other one is wavy. Reynolds number is 1000 and transmembrane pressure is 1 bar for both membranes. So everything is the same, except one is flat and one is wavy. And we do two fouling cycles here. One pure water permeance, so you obtain a flat value for the permeance. Then we switch to the oil and water emulsion. You see that the permeance decreases because of fouling. You then reach a plateau of the membrane that is fouled, and then we switch to pure water to clean the membrane, and you can see that there is a partial recovery here, but not all the initial permeance, so there is some irreversible fouling, and then you run the cycle again. And you can see that for the flat membrane, essentially after when you go to the second fouling cycle, the membrane is completely fouled and there's pretty much no permeance left. Whereas with the wavy membrane, you do the first fouling cycle. Of course, you have a loss due to fouling, but then when you clean with pure water, you recover most of the initial permeance. Not all, but a significant percentage. You then do the second fouling cycle, and again you recover more or less the same percentage. So these are the definitions of reversible and irreversible components of fouling, but I want to highlight some data in the table that you find below. First of all, and some of you might have noticed this from the plots in the previous slide, the wavy membrane has a higher permeance in LMH per bar than the flat membrane, even though they have the exact same footprint. So the membranes are 47 millimeter in diameter and fit in a standard cross-flow cell. The reason for the higher permeance of the wavy membrane is that because it is wavy, it actually has a higher surface area within the same footprint. So this is an added bonus, if you want, of the 3D printing, using 3D printed structures, in that you're adding a third dimension to a membrane, which is otherwise is flat or 2D. You can see that they have the same rejection because this is given by the PS layer. But what is interesting is that the recovery of the permeance for the wavy membrane is 71%, whereas for the flat membrane it's only 37%. And in the reversible fouling is 10% for the wavy membrane, but 63% for the flat membrane. So this is very clear evidence that the wavy structure not only slows down the accumulation of fouling, but makes it easier to dislodge the fouling what has formed. Some fouling will form anyway, that's just inevitable, but the wavy structure slows down the accumulation of fouling and makes it easier to dislodge once it has the fouling layer has formed. So we then did, if you look at the top left plot, we actually did 6 fouling cycles: pure water, oil and water, and then switch to pure water to clean. And you can see with the wavy membrane, we managed to get some permeance until about the 4th cycle, after which the membrane is fouled. Remember that with the flat membrane, you lost everything after the first cycle. There was no permeance after the first cycle. At the bottom ones, these are the components of reversible and irreversible fouling. It's more or less what I already mentioned before. You can find more details in the paper below. What we also did is to look at some cleaning agents. So as I mentioned, with the data I've shown you before is only using water as a cleaning agent. We were able to recover only part of the irreversible fouling for the wavy membrane, even though that was a very small component. We then tried some common cleaning agents, and it was possible to recover a significant higher proportion. So by using a wavy membrane and a cleaning agent, you can actually go pretty much to almost initial permeance. And again, with the flat membrane, you actually do recover less, because the wavy structure not only decreases the amount of fouling that is accumulated, but that localized turbulence makes it easier to dislodge that fouling that has already accumulated. And we then switch from oil and water to BSA, because that is a very classical, let's say, foulant that represents biological fouling. So here is a similar experiment. In blue, you have the flat membranes. In red, you have the wavy ones. And you have the same behavior. Initial decrease in permeance due to fouling when you switch to BSA. We keep the fouling, the BSA, ongoing, in this case, for 60 minutes. Then we switch to pure water permeance. And you can see that, again, with the wavy membrane, there's significant recovery, whereas with the flat membrane, you essentially go almost towards no permeance. You can see, quite interestingly, that the recovery of pure water permeance between fourth, third, and second cycle is actually quite constant once you lost a little bit after the first cycle. So we actually performed the test for 10 cycles, and you can see that after you have a loss in the first cycle, you have pretty much constant performance for 10 fouling cycles. BSA, pure water cleaning, BSA, pure water cleaning, etc. So this is really interesting, because essentially you have a membrane that once it's lost, once you form an initial fouling layer, essentially is a membrane that doesn't foul anymore. And that is because of the wavy structure. So this is very interesting, and it could be a way to extend, significantly extend the performance of a membrane process using a very common material like PS, but only giving it structure. If you want to know more about this work, this is a paper we published in Applied Material Interfaces in 2019. Let me come now to more recent work we've done on 3D printed nanofiltration membranes. So when we started doing this, we had a practical problem. So your 3D printer has resolution limits. And so you have these large pores in a 3D printer, but then you have this very thin selective layer, for example, PVDF, which has 2 nanometer pores, is only a few micrometers thick, and it should bridge the gap between this huge pore in the 3D printed support. And fundamentally, it didn't work. What you see here, this is a cross-section of a 3D printed membrane. This part here is the 3D printed support. This brighter area is the PVDF nanofiltration layer. And you can see that the layer has broken down and collapsed into the pores of the membrane. Or if it doesn't break down, it delaminates, as you can see here. This is the support, this is the pore of the support, and this is the layer. So we had to think of a different approach for to make nanofiltration membranes using this technology. And actually, we took inspiration from the way you make a thin film composite membrane. As you know, in a TFC membrane, you have the selective layer, you have the support, which is a very large porosity to limit resistance. And then you have an interlayer which bridges the gap between the very small porosity of the selective layer and the large pores of the support layer. And so we did the same thing with the 3D printed support, but rather than having two separate objects, the support and interlayer, we actually 3D printed a single object, one where the bottom part has these very large pores of 300 microns, and the top part, which is this one here, or seen here, has no designed pores. So it's not porous in the sense that we did not design pores as we did here, but still has some porosity, which comes from the way we designed it. And let me explain a bit more. You will remember what I showed you at the start, that the digital resolution of the membrane affects what gets printed. And if you look at these images at the bottom, this is the same object, but at the left you have a much lower resolution, and you see a lot of more white spots, which are essentially porosity, than you see on the right, where is it much more uniform structure. So what we did is we manipulated the CAD file for the top part of this single 3D printed object to have no designed pore, but to still have some porosity that is small enough to support a selective layer in the nanofiltration range. So just to reiterate, this is a single object that has a bottom part with designed large pores of 300 micron, and the top part which has no designed porosity, but still has some porosity coming from the way we manipulated the 3D printed digital file. So then what we did is we printed the object, this asymmetric support, and we did then do a selective layer by coating polydopamine on PVDF. We then applied the selective layer onto the membrane, do vacuum suction, and it forms a very nice conformal coating onto the support. And this is the result you get. Here at the top left, you see a micrograph from the top of the complete membrane, and you can see that there is the selective layer is clearly following the shape of the underlying support with peaks, with peaks and troughs. And here you have a cross section of the membrane. The middle SEM micrographs are of the selective layer, so it's about 120 nanometer, 130 nanometer thick polydopamine on PVDF. And at the bottom left, you have the final membrane, where again you can clearly see that the nanofiltration selective layer makes a conformal coating on top of the 3D printed support. Okay, so let's look at some results. So this is the pure water permeance. The dots are experimental data, and the solid curves are from computational fluid dynamics simulations. So this is the time zero, is the pure water permeance. And again, you see that the wavy membrane in red has a higher starting permeance or pure water permeance than the flat membrane because of the higher surface area within the same footprint. And then here we use some dyes, and you can see that the permeance decreases because of fouling. What you see here, we tried 4 different dyes, and what you see here is dye rejection. In red, the columns in red are for the wavy composite membrane with the nanofiltration layer. And in blue, now you have actually the wavy composite membrane with PVDF alone. So this is ultrafiltration, whereas the PVDF polydopamine is nanofiltration. And in fact, you see that the wavy membrane with the nanofiltration PVDF polydopamine selective layer has more than 90% rejection with rhodamine blue and chromium red, and just shy of 90% with with acid red. So the molecular weight cutoff is around 550 Daltons. And I would like to highlight that because we are using dyes, and there's always the risk of having adsorption rather than rejection, we did mass balances in all our tests. The mass balance is always more than 97%. So this is actually rejection data and not adsorption data, as you find in many publications that look at use dyes to see the performance of the membrane, but instead they're actually doing absorption of the dyes on the membrane. So what we then did is to look actually at both charged dyes and salts and look at concentration polarization. So here you have 4 plots. Let's start from let's actually start from the top two, the top two relate to mass transfer resistance. The red curves are all for the wavy membrane, and the blue curve are for the flat membrane. And in general, you see that the wavy membrane has better transport properties than the wavy membrane. But what I would like to highlight is the 2 plots at the bottom. Let's go with the bottom left. This is the concentration polarization factor. So the higher it is, the worse is the concentration polarization effect. And you can see that for the wavy membrane, you have a significant less concentration polarization buildup than for the flat membrane. Again, the dots are experimental data, and the curves are the CFD modeling. And at the bottom right, you have a summary of mass transfer coefficient and concentration polarization factor. And you can see that in the case of the wavy membrane, you have high mass transfer coefficient, low CP factor, and of course, the opposite is for the flat membrane. So in fact, the wavy membrane can significantly reduce the concentration polarization when dealing with charged probe molecules. Again, remember, flat membrane, wavy membrane both have the exact same selective layer, which is a PVDF polydopamine nanofiltration thin selective layer. To give you some numbers, the mass transfer coefficient is nearly triple that of the flat membrane, and the CP factor is about 57% lower for the wavy surface than the flat one. And the reason is, again, if I go back to those images I showed you initially of the CFD streamline velocity field, is because you're generating this turbulence, in this case, in one of the troughs of the wavy membrane, and this recirculation helps lift off any particle or charged particle that has accumulated on the surface of the membrane, which is this represented by this double line here. So of course you have the permeate that goes through the membrane and the fouling that accumulates on the feed side of the membrane. Okay, so let me go towards conclusion. The first thing is that 3D printing offers fantastic opportunities to design novel membrane structures, complex shapes, function, and using a broader range of materials than what we are used to with traditional membrane fabrication techniques. However, there are limitations, and by working around and with these, we were able to fabricate both ultrafiltration and nanofiltration composite membranes by depositing a selective layer onto 3D printed support. And the wavy structure significantly outperforms flat membranes with reduced fouling buildup and reduced concentration polarization when you go to NF region and charged probe particles. Mm-hmm. With this, I would like to thank my research group, who are the ones who have done all this wonderful work that I get to talk about, and our funders, in particular the EPSRC, that has funded the vast majority of this work. And with this, I'd like to conclude just by saying that if any of you is interested to get in touch, this is my email. I'm very happy to talk about the results I've discussed about today. Thank you. So now I'll stop. Okay. Marco, I think you're on mute.
Yes, I have my microphone muted. I'm sorry, because today I'm acting as chair and technical guy behind the streaming. So indeed, I'm facing some difficulty making both jobs. But I think that your outstanding presentation and the message of your work, innovative work, I must say, very innovative work, you have performed and you are continuing to perform. Surely has arrived to the audience.
Thank you.
I'm very fascinated by the idea to build up membranes by 3D printing, and I'm happy to see that the efforts you are delivering in this topic are providing more and more important results. Trying to live together with the limitations the technology has to make a nanofiltration membrane out of this. This is something that no, it's quite a good job. I think that perhaps one day we can dream to arrive to a reverse osmosis membrane for desalination by 3D printing, and this will be, and also the possibility, to design pore patterns or membrane surfaces. This is, I remember work from our colleague, Professor Wessling, about this, who performed this kind of very organized porous structures 15 years ago, something like this. And for some applications, these membranes are outstanding. For other applications, Davide, in particular, something of interest of you, wastewater treatment, I think that the fouling might be too much in these kind of structured pores membranes. This is the same difficulty which was encountered 15 years ago, and so I think that it might be also a good idea to take this work from the past and to collect the ideas from the past in your present work. I'm checking the chat. Strangely enough, I must say, there are no questions, pending questions, so I invite the audience to write on the chat, making, if possible, their comments, or I have to check. Again, I have to make also the technical part. I'm checking if they're allowed to write to the chat, because I think it's very strange, this kind of, so I'm checking. I think they should, yes. I think they should be able. If not, there is a new option which do not allow, which I don't know, because the streaming platform has changed a bit their layout, and so perhaps there is a new option I'm not aware of.
I think a question has come.
I know,
Marco, yes.
Anthony assisted me in this strange situation, so indeed he is able to
Oh, wow.
something.
Okay.
And okay, you can read it on the screen. He asks you about how do you cast the UF selective layer on the Wi-Fi support.
Yeah. So when we started doing this, thank you, Anthony, for the question. We actually used a very basic vacuum filtration setup. So we put the selective layer on top of the 3D printed support, and then we apply vacuum. And it works surprisingly well in terms of the stability of the membrane, in part because of the chemical compatibility between the selective layer and the material of the 3D printed support. Of course, unless you do chemical cross-linking, you can't do backflashing. So if we try to do backflashing, the membrane will delaminate, but then that is a common problem with thin film composite membranes. So it works in the same way. More recently, we have acquired a slightly more sophisticated system to make a conformal coating of the selective layer onto the 3D printed support, one that applies a little bit of heat, nothing that modifies the structure of the membrane, but just enough to give that little extra pliability to get even a better conformal coating. But even just vacuum filtration works very well.
Okay, thank you very much. In name of our audience and of Anthony. We wait a couple of minutes for another question in case it arrives. One curiosity,
Yes.
the economical benefits of all this, no? Because the technical ones are growing, are in progress of being analyzed, understanding, and has to be improved.
Yeah.
But do you think we can meet also great economical advantages as this, as for example, it is in the case of 3D house printing or something like this? No, it's there are some very big advantages also from an economic point of view. And in case, if you think that this effectively can have a market, general market or specialized market?
Okay, so I think that for what I show you specifically related to fouling, the advantage is, let's say, reduced operational costs. Now, I think that there are actually uses of 3D printing for commercial products at an industrial scale. As an example, a big sports shoes company actually 3D prints shoes, and they've made a big publicity of that. So you can make them commercially in hundreds of thousands of parts. I think the challenge is that this goes a little bit. Perhaps it's not necessarily compatible with current methods of making, say, a flat sheet membrane in a roll-to-roll process, because the 3D printed objects are discrete, whereas in a sense you're making a continuous membrane. So there will be some work to do there if it is actually worth it. We haven't done a techno-economic analysis on in terms of the additional cost of the 3D printed part in terms of the actual cost of the membrane. However, in general, the cost of the membrane itself is actually relatively secondary to the operational costs over the lifetime of membrane. So going on the operational costs, particularly if you can increase the distance between cleaning cycles, so you extend the operational cycle of a membrane, or you can reduce the amount of cleaning solvents solutions, or the level of, say, toxic chemicals I need to use. That again is sort of economic and environmental savings. But all I'm saying is qualitative, because we haven't done a techno-economic assessment of this.
Davide, one more question, and then there is another question from the audience.
Yeah.
Are you able, or are you thinking to be able to print membrane modules. You print the membrane you print the membrane within a printed membrane modules, and you make a cartridge or something like this.
Yes, so we've thought very much about that, and in fact we've done this for a slightly different thing as for a membrane contactor. So we thought about doing this, and the interesting thing is that now there are 3D printers that allow you to print different materials in the same object. So you could imagine, for example, of printing a polymeric support but a metallic module. So there's a lot of possibilities. So we haven't done this, but this is a very nice idea that you could get the whole object. And if you go the next step, if you are printing the whole membrane plus module, you actually get free of the limited shapes we normally make membranes in, like a hollow fiber in the module, is a cylinder, or your spiral wound again is a cylinder. You could make something that is conformal to a shape in a constricted area, like could be a space station or in a submarine where space is at a premium. So you can imagine using the advantage of 3D printing, which is the ability to make unusual complex shapes, and adapt that to a membrane fabrication process, which you otherwise can't really get.
Amazing. Next question. Patrick asking, what should be the properties of a polymer to be able to perform the 3D printing?
Okay, so actually, this is an interesting aspect, I think, of 3D printing, in that you can print a much wider variety of materials than the one we are used to deal with when we normally make membranes. So the answer is pretty much almost any polymer, but also ceramic material. So one of the things we're doing right now, we actually have a 3D printer that allows us to print ceramic objects using metal oxide powders and the polymer binder. And then you print the object, you burn away the polymer binder, and you have a solid ceramic object. So in practice, as long as you can solubilize a polymer and make a paste or a slurry, and then you can print it. There's a lot of work on optimization, working on the viscosity and the rheology of that, say, polymer or a ceramic paste, because once you print it out, you want it to retain the shape and not collapse. So you cannot have something that is too liquid because it will not keep the shape. So there's a lot of work, very classical polymer rheology work to do, but you can use pretty much any polymer that you can, I would say, solubilize.
Thank you. And I hope to get the name correct. Kirong asking, thanking you about the talk, and asking, since we're already a wavy structure on the NF membrane, it is necessary to use a spacer, and in case, how to integrate it with a spacer?
That's a very good question. So we use a standard module, sort of Sterlitech type 47 millimeter crossflow, and that has a space between the top and the bottom of the module of I think is in the order of 2-3 millimeters, something like that. So we fabricated our membrane to be very well within that space, and so that did not affect, in a sense, the performance of the membrane. But as I was saying earlier with the module, you could very easily print in the same material a spacer on top of the 3D printed object in the same print. So that's something really easy to add. I think with the technology we used, which is to have a selective layer on top of a 3D printed layer, 3D printed support, you need, in a sense, to have an open structure to have the one go on top of the other. When we get perhaps to the point where we can directly 3D print the membrane, then all of these advantages can be, you can use these advantages just as an example, the concept I shared earlier of having a porous, non-porous layer where you don't have any intended pore, designed pore, but you still have some porosity. There's a very nice paper from Bart van der Bruggen group a few years ago where they used this sort of residual porosity for gas separation. And so there, you could directly print membrane with spacer and module without any intermediate step.
Okay, thank you very much. There are no questions left, so I thank again the audience being here, and in particular I thank Professor Davide Mattia having told us about his outstanding research and the results he got during his work in such a clear way. So thank you very much all of being here, and I hope to see you all at the next EMS webinar and
Marco,
at EMS congresses, of course.
Marco, let me allow you to thank you for chairing the session, and again the EMS Council for this great opportunity. It's been a pleasure. Thank you very much.
Yes, you know the EMS Council well, since you were a member in the past of the council. So the gratitude also of the council goes to you of the work you've performed in the past and also actually. Okay, Davide,
thank you,
thank you
and
very
see
much.
you soon, hopefully at Euromembrane. Yeah.
We see us soon at congresses. The next one is Euromembrane 2022. Yeah. Will you be there?
I will, yes. So I'll see you.
Okay, so we meet there, and I hope to meet all other EMS members at this congress very soon.
Sounds great. Thank you very much. Take care.
Have a nice day.
Bye.